Hi there, you're in the lab with mate JJ. Today is Old Book Teardown Day. We're going to be tearing down an old book. So the job title for today is Ohm Oracle, today on the Ohm Oracle. And the book we'll be looking at today is this old thing, Electronic and Radio Engineering by Frederick E. Terman, published by McGraw-Hill, and this is the 4th edition. This one is a hardcover with a plastic dust jacket that's been lovingly sticky taped on here. Looks like decades upon decades ago. If you studied electrical engineering back in the good old days, then you would have been reading Terman, Frederick Emmons Terman. He was the sort of he was the main author back in the day. This book was published in 1955. It's a long time ago. It had the assistance of some other people. We'll see about that in a minute. So yeah, today we'll just be having a flip through this thing, trying to have a bit of a squiz at what it covers. Of course, we won't be looking at it in depth. We'll just be flipping through. So I suppose there's no reason to not just jump over to the bench and have a look in this thing. All right. Well, here we are on the bench. This is our tome. McGraw-Hill Electrical and Electronic Engineering Series. And this is, as we said, Frederick E. Terman, Electronic and Radio Engineering, McGraw-Hill, 4th edition. There's a number on the back here, 63510. Don't know what that means. And here we go. And this looks like it belongs to one J. Rowe of 19 Rees Avenue, Belmore. Belmore's a suburb in Greater Sydney, I believe. I don't know Belmore. I've heard of Belmore. I don't know where it is. I'm just trying to get this out here. Come on. Come on. Dear me. There we go. All right. Electronic and Radio Engineering. Now this is part of the McGraw-Hill Electrical and Electronic Engineering series. And the consulting editor was our very own Frederick Emmons Terman himself, with associate consulting editors Harman and Truxell. And then they list all of the books in their electronical and electronic engineering series. This is a great big long list of subjects. I've just realized I'm going to need more coffee to get through this. I'm going to make coffee. I'll be back. Okay, got myself a coffee, got myself a bottle of water. I am ready to do this. So I wonder how long this is going to take. I guess we'll find out. So let's have a squiz at this series, huh? What have we got? I don't know how many is there. It looks like 30, 40, 50, I don't know. So what are the topics? Alternating current machinery, acoustics, analysis of feedback control systems, theory and application of industrial electronics, synthesis of linear communication networks, volumes 1 and 2, harmonics, sidebands and transients in communication engineering, introduction to nonlinear analysis, fundamentals of vacuum tubes, control system dynamics, foundations of information theory. Feinstein, haven't heard of him before. Basic electrical engineering, electric machinery, basic electron tubes, fundamentals of television engineering, engineering electronics, fundamentals of electronic motion, introduction to electromagnetic engineering, engineering electromagnetics, fundamentals of electrical engineering, electronics in engineering, transmission lines and networks, antennas, electromagnetics, analysis of alternating current circuits, general network analysis, electronics, pulse and digital circuits, introduction to electric fields, transient performance of electric power systems, engineering electronics, electron tube circuits, electronic engineering, introduction to electromagnetic fields, radio electronics, direct current machinery, electric transmission lines, transient electric currents, fundamentals of electron devices, vacuum tubes, elements of power system analysis, passive network synthesis, electronic and radio engineering. That's this book. Okay. And electronic measurements, elements of servo mechanism theory, servo mechanism analysis, alternating current and transient circuit analysis, and automatic feedback control system synthesis. There you go. So this is, of course, Frederick Emmons Terman, Professor of Electrical Engineering, Dean of the School of Engineering, Stanford University. There you go. Assisted by Robert Arthur Helliwell, Associate Professor of Electrical Engineering at Stanford University, Joseph Mayo Petit, Professor of Electrical Engineering at Stanford University, Dean Alan Watkins, Associate Professor of Electrical Engineering at Stanford University, and William Ralph Rambo. Haha, this guy's name is Rambo. Associate Director, Applied Electronics Laboratory, Stanford University. So it's Terman and his mates from Stanford have put this book together. Wonderful. This is the 4th edition, published by McGraw-Hill Book Company Incorporated, New York, Toronto, London, 1955. Electronic and Radio Engineering, copyright 1955 by the McGraw-Hill Book Company, copyright 1932, 1937, 1947 by the McGraw-Hill Book Company, printed in the United States of America. Blah, 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 blah. There's a catalog number. Great. So it looks like this the first 3 versions. The first one came out in 1932, then again in 1937, then 1947, and then 1955. So that was a long time, wasn't it? Wow. All right. So this is the preface to the 4th edition. This 4th edition has the same objective as the 3 prior editions, namely to provide a text and reference book that summarizes in easily understandable terms those principles and techniques which are the basic tools of the electronic and radio engineer. In keeping with current trends, increased emphasis is placed on the general techniques of electronics without regard to the extent of their use in radio systems. This change is reflected in the new title, Electronic and Radio Engineering, which is more descriptive of the subject matter actually covered in the present volume than is the previous title, Radio Engineering. Ah, I see. Cool. All right. So this is okay, because we already read Radio Engineering. Let me just check. Hang on. Okay, that makes a whole lot of sense. So Terman had a book called Radio Engineering. That was what it was called for the previous 3 editions, and they added electronic and in front of it for this 4th edition. We actually covered the 3rd edition in July 2024. So a couple of years ago on the channel, we had a look at Terman's Radio Engineering 3rd edition. So this is the 4th edition of that book. There you go, with the new title, and that explains why there wasn't two references to Terman's books here, just the one. So okay, good. Well, now we know that. The keynote continues to be thorough coverage combined with a presentation that allows the reader to study a particular topic without having to read the entire book. The level of presentation, particularly the mathematical level, remains unchanged. Thus, the present volume is designed to serve as a text and reference for the same clientele that found the previous edition so useful. To keep pace with the rapidly advancing technology, new material has been added in practically every chapter. More than half the illustrations are new, and all have been redrawn to conform to new graphics standards. A new chapter dealing with microwave tubes makes available for the first time an explanation in simple language of the basic mechanism of operation of traveling wave tubes and backward wave oscillators, carcinotrons. In the treatment of wideband video and tune amplifiers, primary emphasis is placed on the rise time, overshoot, and sag, since these characteristics are more indicative of the performance under actual conditions than is the older approach in terms of amplitude and phase behavior as a function of frequency. The material on nonlinear waveforms and pulse techniques has been greatly expanded to provide more complete coverage of this important aspect of electronics. The chapter on television has been thoroughly revised, and a compact and simple explanation is given of the system of colored television, now standard in the United States. Increased attention is also placed on propagation phenomena involving the troposphere. Of particular importance is the chapter on transistors and related semiconductor devices, one of the longest in the book. Here is presented a simple, straightforward explanation of the basic phenomena occurring inside the transistor and of how these phenomena lead to the terminal characteristics. This treatment is such that it can be understood by undergraduate students. At the same time, it is sufficiently complete and fundamental to provide a firm foundation for further study of this new and very important subject. Special attention has been given to the needs of the teacher. Because of the growth of electronics, it is no longer possible to cover every important topic adequately in a one-year course. Electronic and radio engineering provides the instructor with an opportunity to select those topics which he himself wishes to emphasize, and at the same time provides the students with a reference book of comprehensive coverage and continuing value. It will be observed that the book breaks down into three distinct parts, namely a group of chapters dealing with circuits, components, resonant circuits, transmission lines, waveguides, and cavity resonators. A group of chapters concerned with fundamentals of electronic engineering, vacuum tubes, transistors, amplifiers, oscillators, modulators, detectors, nonlinear waveforms, etc., which are the heart of the book, and a concluding group of chapters concerned with radio systems and radio engineering, antennas, propagation, transmitters, receivers, television, radar, and radio aids to navigation. Thus, an instructor can, if he desires, concentrate on the material concerned with fundamental electronics and regard the remaining subject matter as available to the student should he need to extend his knowledge at a future date. Alternatively, the instructor can choose to cover a series of selected topics, for example, waveguides, wideband systems, pulse circuits, television, etc. Another possibility is to concentrate on the material primarily with radio systems. Many other combinations are, of course, possible. An important feature for the teacher is the more than 1,250 problems and exercises. Many of these involve numerical calculations, but more than half of them are thought questions that will require the student to give further consideration to topics covered in the text. Such exercises can be used to extend and solidify the student's knowledge. They are also suggestive of questions suitable for use on examinations. The number of problems and exercises is so large that the same problem need not be assigned to a class more often than once every 2 or 3 years. The collaborators listed on the title page have made important contributions to the preparation of this volume. Dr. Helliwell worked on the sections dealing with ionospheric propagation. Dr. Petit is in large measure responsible for the general character of the chapter dealing with transistors and semiconductors. The treatment of traveling wave tubes and backward wave oscillators is due to Dr. Watkins. William Rambo prepared and the background material used in revising the presentation on radar. In addition, acknowledgement is made to Dr. B.H. Wadier, Bruno, and blah, 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 graduate students for assistance in preparing illustrations. There we go. Frederick Emmons Terman. So that was the preface to the 4th edition. They didn't publish the preface to the previous editions. All right, here we go. Contents. Preface, we just read it. Chapter 1. The elements of a system of radio communication. Circuit elements and circuit theory. Circuit elements. Properties of circuits with lumped constants, transmission lines, waveguides and cavity resonators. Electronic engineering fundamentals. Fundamental properties of electron tubes, electron optics and cathode ray tubes, voltage amplifiers for audio frequencies, voltage amplifiers for video frequencies, amplifier distortion, power amplifiers and amplifier systems, negative feedback in amplifiers, tuned voltage amplifiers, tuned power amplifiers, vacuum tube oscillators, amplitude modulation, detectors and mixers, frequency modulation, wave shaping, nonlinear waves and pulse techniques, microwave tubes, power for operating vacuum tubes, transistors and related semiconductor devices. Wow. Radio engineering and radio systems. Propagation of radio waves, antennas, radio transmitters, receivers and communication systems, television, radar and radio aids to navigation. The index begins on, the name index begins on 1057, page 1057, and the subject index on page 1061. Okay, cool. Well, that's a very terse table of contents, isn't it? Oh, I see. Right. I'm going to run over that again. So that was, okay, so this is the chapter 1 to 26, and these are the 3 lumped chapters. What did he say? They were lumped together. It will be observed that the book breaks down into 3 distinct parts, namely, okay, thought he said lumped. I don't know where I got that from. Oh, there was the reference to lumped. I got my wires crossed. All right, so we're going to be looking at circuit elements and circuit theory, then electronic engineering fundamentals is the main game, and then there's some radio engineering and radio system stuff in the back end of the book. So it's changed its emphasis from radio to electronics. Fair enough. All right, and here we go, straight into it. Chapter 1, the elements of a system of radio communication. Okay. I'm talking about how radio waves propagate. Electrical energy that has escaped into free space exists in the form of electromagnetic waves. These waves, which are commonly called radio waves, travel with the velocity of light and consist of magnetic and electric fields that are at right angles to each other and also at right angles to the direction of travel. If these electric and magnetic fluxes could actually be seen, the wave would have the appearance indicated in figure 1.1. 1/2 of the electrical energy contained in the wave exists in the form of electrostatic energy, while the remaining half is in the form of magnetic energy. The essential properties of a radio wave are the frequency, intensity, direction of travel, and plane of polarization. The radio waves produced by an alternating current will vary in intensity with the frequency of the current and will therefore be alternately positive and negative as shown in figure 1.1b. The distance occupied by one complete cycle of such an alternating wave is equal to the velocity of the wave divided by the number of cycles that are sent out each second, and is called the wavelength. The relation between the wavelength lambda in meters and frequency f in cycles per second is therefore as given. That number on the top there, that's the speed of light. The quantity 300 million is the velocity of light in meters per second, roughly. The frequency is ordinarily expressed in kilocycles, abbreviated kc, or in megacycles, abbreviated MC. There you go. And of course, we now call them hertz in memory of the scientist Hertz. So in 1955, I guess that tradition hadn't been started yet. So they were just called cycles, not hertz, but they're called hertz now. A low frequency wave is seen from equation 1-1. Where's equation 1-1? Did you see that? I didn't see it. And these pages are really hard to get. Oh, there we go. Of course, yeah, this is the equation. A low frequency wave is seen from equation 1-1 to have a long wavelength, while a high frequency corresponds to a short wavelength. Of course. The strength of a radio wave is measured in terms of the voltage stress produced in space by the electric field of the wave, and it is usually expressed in microvolts, stress per meter. Since the actual stress produced at any point by an alternating wave varies sinusoidally from instant to instant, it is customary to consider the intensity of such a wave to be the effective value of the stress, which is 0.707 times the maximum stress and the atmosphere in the atmosphere during the cycle. The strength of the wave measured in terms of microvolts per meter of stress in space is also exactly the same voltage that the magnetic flux of the wave induces in a conductor 1 meter long when sweeping across this conductor with the velocity of light. The minimum field strength required to give satisfactory reception of a wave depends upon a number of factors, such as frequency, type of signal involved, and amount of interference present. Under some conditions, radio waves having signal strength as low as 0.1 microvolts per meter are usable. Occasionally, signal strengths exceeding 1000 microvolts per meter are required to ensure entirely satisfactory reception at all times. In most cases, the weakest useful signal strength lies somewhere between these extremes. All right, and off we go. Got a table here. Table 1-1, classification of radio waves. We've got very low frequency, medium frequency, high frequency, very high frequency, ultra high frequency, and super high frequency. I would have thought super was less than ultra, wouldn't you? I don't know. Frequencies higher than about 2000 megacycles are frequently referred to as microwave frequencies. Yeah, right. Might as well have a look at the details here. So this is the very low frequency, VLF. The frequency range is 10 to 30 kilocycles, which is hertz. I'll just call it kilocycles, that's fine. The wavelength range is 30 kilometers to 10 kilometers. Okay. Propagation characteristics. Low attenuation at all times of day and of year. Characteristics very reliable. Typical uses: long distance, point-to-point communication. Low frequency, LF, 30 kilocycles to 300 kilocycles, about 10 kilometers to 1 kilometer. Propagation at night, similar to very low frequency, but slightly less reliable. Daytime absorption greater than very low frequency. Typical uses: long distance, point-to-point service, marine and navigational aids. Medium frequency, 300 kilocycles to 3000 kilocycles, and the wavelength being 1 kilometer to 100 meters. Attenuation at night and high in daytime. Okay, the attenuation is low at night and high in daytime. Broadcasting, marine communication, navigation, harbor, telephone, etc. That's the typical use cases for medium frequency waves. High frequency waves, It's 3 megacycles to 30 megacycles, wavelength being 100 meters to 10 meters. Propagation characteristics are transmission over considerable distance, depends solely on the ionosphere, and so varies greatly with time of day, season, and frequency. Typical uses include moderate and long-distance communication of all types. And we've got very high frequency, being 30 megacycles to 300 megacycles, wavelength of 10 meters down to 1 meter. Propagation characteristics, substantially straight line propagation analogous to that of light waves, unaffected by ionosphere. Typical uses: short distance communications, television, frequency modulation, radar, airplane navigation. And we've got ultra high frequency radio waves in the 300 to 3000 megacycle range, which is 100 centimeters down to 10 centimeters, and these have the same propagation characteristics as very high frequency, which is substantially straight line propagation analogous to that of light waves, unaffected by ionosphere. And typical uses: short distance communication, radar, relay systems, television, etc. And then we've got super high frequency, SHF, 3,000 megacycles to 30,000 megacycles, wavelength 10 centimeters down to 1 centimeters. Same propagation characteristics, substantially straight line propagation analogous to that of light waves, unaffected by ionosphere. And typical uses are radar, radio relay, and navigation. There you go. I'm not sure about where Wi-Fi signals exist. I think they're microwaves, aren't they? Let me go and find out. I'll be back. So Wi-Fi starts at 2.4 gigahertz, then goes up to 5 gigahertz, 6 gigahertz, and there are some applications beyond even that. So this is 30,000 megacycles, so that'd fall in there. 2.4 gigahertz is 1,000 million. Yeah. Okay. Every radiator. Every radiator has directional characteristics as a result of which it sends out stronger waves in certain directions than in others. Directional characteristics of antennas are used to concentrate the radiation towards the point to which it is desired to transmit, or to favor reception of energy arriving from a particular direction. All right, this is figure 1.2. It's a diagram showing how a signal may be transmitted by modulating the amplitude of a radio wave, and how the original signal may be recovered from the modulated wave by rectification. For the sake of clarity, the radio frequency is shown as being much lower than would usually be the case. Okay, so here's the amplitude modulated wave, and here is the frequency modulated wave. Figure 1.3, character of waves produced by amplitude modulation and by frequency modulation, where the modulation is sinusoidal in both cases. For the sake of clarity, the radio frequency is shown much lower than would usually be the case. Nature of a modulated wave. Some mathematics here. Okay, the decibels is given as a ratio of powers. The decibel, abbreviated dB, is a logarithmic unit used in communications work to express power ratios. If the powers being compared are P1 and P2, then the decibels equals 10 log 10 P2 divided by P1. The sign associated with the number of decibels indicates which power is greater. Thus, a negative sign means P2 is less than P1. The decibel has no other significance than that given in equation 1.4. Thus, if decibels are used to express amplification, this simply means that the presence of the amplification increases the power output by the number of decibels attributed to the amplification. Again, under many conditions, relative power is proportional to the square of the voltage E, or the current I, or the field B, etc. Under these conditions, the decibels 20 log 10 E2 divided by E1. And also the same, the ratio of currents, the ratio of field. So, and here it's the log of the power, so squared. So that's why the 2 comes down from this. These relations must be used with caution, however, as they hold only when the resistance associated with E2 or I2 or B2 is the same as associated with E1 or I1 or B1. All right, and here we go. Table 1-2, power, voltage, and current ratios for assigned decibel values. Okay. And then decibel equivalent of power, voltage, and current ratios. All right, now we're up to chapter 2, circuit elements. And we're going to start by talking about inductance. Inductance can be defined as the flux linkages per ampere of current producing the flux. The inductance L in henries is the flux linkages divided by the current producing flux times 10 to the minus 8. Calculation of inductance. Figure 2.2, values of constant F for use in equation 2.2 to obtain the inductance of single layer solenoids. Figure 2.3, typical hysteresis loop, showing minor hysteresis loops 1 and 2. Figure 2.4 is a curve giving incremental permeability of typical silicon steel as a function of AC magnetization for several values of superimposed direct current, showing how the inductance decreases with increased DC and reduced AC magnetization. Figure 2.5 is typical magnetic circuit involving a permanent magnet. There's a section on permanent magnets. Figure 2.6, demagnetization and energy product curves of a permanent magnet showing minor hysteresis loop associated with stabilization. Figure 2.7, demagnetization and energy product curves of typical permanent magnet materials. I'm not sure what those materials are. Al-Nico, Vic alloy, Al-Nico 6, 36% cobalt steel, and Al-Nico 12. I don't know what all those materials are. Mutual inductance and coefficient of coupling. Figure 2.8, several simple methods of coupling two circuits. And mutual inductance in henries. Coupling, coefficient of coupling. Okay. Skin effect in coils and conductors at radio frequencies. Figure 2.9, isolated round conductors showing magnetic flux paths and also typical current distributions. Might just read you about skin effect. The effective resistance offered by conductors to radio frequencies is considerably more than the ohmic resistance measured with direct currents. This is because of an action known as skin effect, which causes the current to be concentrated in certain parts of the conductor and leaves the remainder of the cross-section to contribute little or nothing toward carrying the current. A simple example of skin effect, and one that makes its nature clear, is furnished by an isolated round wire. When a current is flowing through such a conductor, the magnetic flux that results is in the form of concentric circles as shown in figure 2.9. It is to be noted that some of this flux exists within the conductor and therefore links with, that is, in circles, current near the center of the conductor, while not linking with current flowing near the surface. The result is that the inductance of the central part of the conductor is greater than the inductance of the part of the conductor near the surface. This is because of the greater number of flux linkages existing in the central region. At radio frequencies, the reactance of this extra inductance is sufficiently great to affect seriously the flow of current, most of which flows along the surface of the conductor where the impedance is low, rather than near the center where the impedance is high. The center part of the conductor, therefore, does not carry its share of the current, and the true or effective resistance is increased, since in effect the useful cross-section of the wire is very, very greatly reduced. The types of current distribution obtained in typical cases of skin effect in a round wire are shown in figure 2.9. When skin effect is present, the current is always redistributed over the conductor whose cross-section in such a way as to make most of the current flow where it is encircled by the smallest number of flux lines. This general principle controls the distribution of current irrespective of the shape of the conductor involved. Thus, with a conductor consisting of a thin flat strip, such as shown in figure 2.10, the current flows primarily along the edges, where it is surrounded by the smallest amount of flux, and the true or effective resistance will be high because most of the strip carries very little current. This illustration makes clear that it is not the amount of conductor surface that determines the resistance to alternating current, but rather the way in which the conductor material is arranged. The ratio that the effective AC resistance bears to the DC resistance of a conductor is commonly called the resistance ratio. It increases with frequency, with conductivity of the conductor material, and with the size of conductor. This results from the fact that at higher frequency, that a higher frequency causes the extra inductance at the center of the conductor to have higher reactance. Similarly, a greater conductivity makes the reactance of the extra inductance of more importance in determining the distribution of current, while a greater cross-section provides a large central region. It is to be noted, however, that a larger conductor always has less radio frequency resistance than a smaller one because, although the ratio of AC to DC resistance is less favorable, it is more than made up by the greater amount of conductor cross-section present. Then they go on to talk about skin effect at high frequencies, some maths over there, capacitors and dielectrics. There we go. So we've got some table 2.1 characteristics of typical dielectrics at radio frequencies with normal room temperature. So we've got air, mica, glass, bakelite, wood, Michalex, steatite materials, polystyrene, polyethylene, and rutile, titanium dioxide. I don't know. Sorry about the pronunciation there. I don't know those materials. Figure 2.12, variation of dielectric constant and power factor of a bipolar dielectric as a function of frequency for two temperatures. Okay. Figure 2.13, equivalent electrical circuits of a variable air condenser. Okay. Condenser is, of course, what they used to call a capacitor. They still call them condenser microphones. Coils for resonant circuits. Okay. Air core coils for resonant circuits. Magnetic cord coils for resonance circuits. Shielding of magnetic and electrostatic fields. Looking at figure 219, paths of electrostatic and magnetic flux lines about the same coil with and without magnetic and non-magnetic shields. Figure 220 is a transformer with electrostatic shield between primary and secondary. Then we've got problems and exercises. How many? 47. 47 exercises. If it is necessary that a magnetic shield for DC fields have a joint, how should the joint be oriented with respect to the direction of the magnetic flux that is being shielded? Oh, wow. I don't know. All right. Chapter 3. Properties of circuits with lumped constants. And there's that word lumped. I saw that at the beginning. Properties of circuits with lumped constants. This is figure 3. One magnitude and phase angle of current in a series resonance circuit as a function of frequency for constant applied voltage and different circuit Qs. So we've got series resonance, analysis of series resonance circuit, universal resonance curve, whole bunch of mathematics there. Figure 3.2, universal resonance curve for series resonance circuit. This curve can also be applied to the parallel resonance circuit by considering the vertical scale to represent the ratio of actual parallel impedance to the parallel impedance at resonance. When applied to parallel circuits, the angles shown in the figure as leading are lagging and vice versa. Working rules for estimating sharpness of resonance. Rule 1, Rule 2. Parallel resonance. Figure 3.3, magnitude and phase angle of impedance of a parallel circuit as a function of frequency for different circuit Qs. Okay. Look at that. E is the voltage applied. ZC equals RC minus J on omega C. Wow. Figure 3.5, forms of parallel resonance circuits involving a shunt resistance and shunt feed. Quantitative relations in parallel resonance circuits with moderate or high Q and the use of universal resonance curve. Parallel resonance circuits with shunt resistances and with parallel feed. As up here it says, consequently, the universal resonance curve and the working rules that were applied for estimating the sharpness of resonance of the series circuit also apply to the case of parallel resonance when the circuit Q is moderate or high. Okay. Figure 3.7, representation of parallel impedance in terms of equivalent series resistance and reactance components, together with universal curve, giving these components as a function of frequency in a parallel resonance circuit having a relatively high Q. On to inductively coupled circuits. This is the theory of inductively coupled circuits. Okay. Inductively coupled circuit as a transformer. Analysis of some simple inductively coupled circuits. Coupled circuit with an untuned secondary consisting of a resistance and inductance. Coupled circuits with untuned primary and tuned secondary. The coupled impedance produced by a tuned secondary circuit consequently varies with frequency according to the same general law as does the parallel impedance of the secondary circuit. Behavior of systems involving resonant primary and resonant secondary circuits. Primary and secondary circuit resonant at the same frequency and having Qs that are equal and not too low. Figure 310, variation of secondary current as a function of frequency in a coupled system in which the secondary is a resonant circuit and the primary is untuned, showing that the secondary circuit follows a resonance curve, which, however, has a lower Q than that of the secondary circuit taken alone. Figure 311, curve showing variation of primary and secondary currents with frequency for different coefficients of coupling when the primary and secondary are separately tuned to the same frequency. Whole bunch of mathematics there. Figure 312. Relative response of a bandpass system provided by two identical circuits critically coupled, together with the resonance curve of a single circuit such as used in the bandpass system. The effects produced by unequal Qs. Coupled resonant circuits tuned to slightly different frequencies. Hence, detuning primary and secondary circuits slightly has approximately the same effect on the shape of the secondary current curve as increasing the coefficient of coupling when there is no detuning. Shunt-fed and shunt-loaded coupled circuits. Figure 316, curves of secondary response when two circuits resonant at the same frequency are coupled together, showing the effective variation of circuits' Qs while maintaining the coefficient of coupling unchanged. The effect of varying Q in coupled systems tuned to the same frequency, with the coefficient of coupling constant. Generalized coupled circuits. We've got figure 317, examples of methods whereby circuits may be coupled. Okay. Direct inductive coupling, capacitive coupling, combined inductive and capacitive coupling, and equivalent circuit. Figure 318, two methods of capacitively coupled two resonant circuits. Two methods of capacitively coupling two resonant circuits. Okay. Figure 39, we've got Thevenin's theorem. Cool. According to Thevenin's theorem, any linear network containing one or more sources of voltage and having two terminals behaves, insofar as a load impedance connected across these terminals is concerned, as though the network and its generators were equivalent to a simple generator having an internal impedance Z and a generated voltage E, where E is the voltage that appears across the terminals when no load impedance is connected, and Z is the impedance that is measured between the terminals when all sources of voltage in the network are short-circuited. There's two notes here, notes 1 and 2. Note 1 says, when the sources of energy in the network are constant current generators instead of constant voltage generators, the internal impedance Z is the impedance observed between the terminals when all constant current generators are open circuit. This is due to the fact that a constant current generator is equivalent to an infinite voltage source having an infinite internal impedance, so that short-circuiting the ultimate source of voltage of the constant current generator still leaves an infinite impedance in the circuit. And 2, An alternative circuit, which is also equivalent to figure 319A, is given in 319C. Here, the network with its generators is replaced by a constant current I that is delivered to a system consisting of the source impedance Z in shunt with which is the load impedance, where I is the output current of the network when the output terminals are short-circuited. This is I equals E divided by Z, which is Ohm's law. The equivalence of the arrangement at A and C in figure 319 is sometimes referred to as Norton's theorem. Well, we always call it Norton's theorem now, I guess. That's what we do these days. So this is figure 319, diagrams illustrating how Thevenin's and Norton's theorems can be used to simplify complicated network containing generators. There you go. Of course, we're learning about that at the moment in Learning the Art of Electronics, aren't we? If you've been following along. So now we're doing impedance matching, and then we're off problems and exercises. Plot a graph of the equation of A showing that P divided by P max versus R divided by RS, where P is the actual power when the load resistance is R and P max is the power blah blah blah. By how many decibels is the power reduced for the following cases of mismatch? All right, chapter 4, transmission lines. Voltage and current relations on radio frequency transmission lines in terms of traveling waves. Interpretation of transmission line equation in terms of traveling waves. The incident wave. The reflected wave. Relation of incident and reflected waves, reflection coefficient. Transmission line constants. Line voltage and current. Examples of voltage and current distributions on transmission lines. Transmission line with open circuit load. Transmission line with short-circuited load. This is figure 4.3, vector diagram showing manner in which the incident and reflected waves combined to produce a voltage distribution on the transmission line. The cases shown correspond to a reflection in which the phase of the voltage is unchanged by reflection. It is also assumed that the attenuation of the line is quite small. Figure 4.4, types of voltage and current distributions produced on a transmission line by different load impedances. It is assumed that the transmission line has low attenuation and a characteristic impedance that is resistive. Characteristic impedance load. Intermediate values of load impedance. Reactive loads. Figure 4.5, phase relations on a transmission line for two typical conditions. In these curves, the voltage of the incident wave at the load is used as the reference phase, and the line attenuation is assumed to be small. The effect of attenuation on voltage and current distribution. Transmission lines with zero losses. Standing wave ratio. Impedance and power factor relations in transmission lines. Figure 4.10, magnitude and power factor of line impedance with increasing distance from the load for load impedances that are, respectively, a resistance less than the characteristic impedance and a short circuit. These diagrams assume that the attenuation of the line is small. Figure 4.11, effect of variation in frequency on the magnitude and phase of the sending end impedance of a short-circuited transmission line of fixed length. Transmission line charts, the Smith chart. The various properties of a transmission line can be presented graphically in an almost endless variety of charts. The most useful graphical representations, however, are those which give the impedance relations that exist along a lossless line for different load conditions. The Smith chart, shown in figure 412, is the most widely used transmission line chart of this class. The diagram is based on two sets of orthogonal circles. One set represents the ratio R divided by Z0, where R is the resistant component of the line impedance and Z0 is the characteristic impedance, which for a lossless line is a resistance. So here's a Smith chart. There we go. You might have seen those before. I've seen them. I don't really understand them yet. But radio's not my bag, man. So maybe I'll learn something about it. But yeah, there we go. This is the Smith chart. So we're going to talk about the effect of line attenuation, impedance measurements using standing wave ratios, equipment for experimental determination of standing wave ratio for impedance measurements. This is figure 414, details of a slotted line type of standing wave detector for a coaxial line. Looks complicated. Transmission lines as resonant circuits and as circuit elements. Figure 416, impedance matching by means of a short-circuited stub line. Although the arrangement shown is a two-wire system, coaxial lines may be employed. Figure 419, double slug system for impedance matching in a concentric line system. Non-reflecting terminations for ultra-high frequency and microwave transmission lines. Artificial lines. An artificial line is a four-terminal network composed of resistance, inductance, and capacitance elements. Insofar as the terminals are concerned, such a network can be considered as being the equivalent of some transmission line when symmetrical about the midpoint, or a combination of a transmission line and a transformer when unsymmetrical. Design of T and pi reactive networks. Directional couplers. Loop type directional coupler. Figure 423, loop type of directional coupler for coaxial line together with equivalent circuits that take into account the effects produced by the electric and magnetic fields on the primary line. There's a two-hole coupler. Directivity and coupling in directional couplers. Miscellaneous aspects of transmission lines. Transmission line irregularities, discontinuity capacitance, tapered transmission lines, we're up to problems and exercises, to chapter 5. Just going to take a break, get some more coffee. All right, on we go with chapter 5. This is waveguides and cavity resonators. Waveguides, general considerations. A hollow conducting tube used to transmit electromagnetic waves is termed a waveguide. At ultra-high and microwave frequencies, waveguides provide a practical alternative to transmission lines for the transmission of electrical energy. Any configuration of electric and magnetic fields that exists inside a waveguide must be a solution of Maxwell's equations. In addition, these fields must satisfy the boundary conditions imposed by the walls of the guide. To the extent that the walls are perfect conductors, there can therefore be no tangential component of electric field at the walls. Many different field configurations can be found that meet these requirements. Each such configuration is termed a mode. Okay. A critical examination of the various possible field configurations or modes that can exist in a waveguide reveals that they all belong to one or the other of two fundamental types. In one type, the electric field is everywhere transverse to the axis of the guide and has no component anywhere in the direction of the guide axis. The associated magnetic field does, however, have a component in the direction of the axis. Modes of this type are termed transverse electric or TE modes, also sometimes called H modes. In the other type of distribution, the situation with respect to the fields is reversed, the magnetic field being everywhere transverse to the guide axis, while at some places the electric field has components in the actual direction. Modes of this type are termed transverse magnetic or TM modes, also sometimes called E modes. The different modes of each class are designated by double subscripts such as TE10 as explained below. Okay, rectangular waveguides. Field configuration of the dominant mode in a rectangular waveguide. A couple of figures here. Figure 5.1, rectangular waveguide illustrating notation. Okay. And then we've got figure 5.2, field configuration of the dominant or TE10 mode in a rectangular waveguide. Guide wavelength, phase constant, group, and phase velocity. Phase velocity. Currents in waveguide walls. Coupling and leakage through slots and holes in waveguide walls. Attenuation. Higher modes in rectangular waveguides. Generation of different waveguide modes. Rectangular waveguide with vertical stub posts extending into the guide from the top and bottom sides. Suppression of unwanted modes. Physical picture of propagation in a rectangular waveguides, or in rectangular waveguides. Figure 5.12, steps involved in building up a physical picture of propagation in a rectangular waveguide. Figure 5.13, paths followed by a wave travelling back and forth between the sides of a waveguide for values of free space wavelengths differing from the cutoff wavelengths by various amounts. Circular waveguides. Figure 5.15, field configuration of the dominant TE11 mode and of the first few higher order modes in a circular waveguide. Figure 5.16, attenuation as a function of frequency of the dominant and first higher order mode in a particular circular waveguide with copper walls. Reflected and incident waves, field distributions, and standing wave ratio in waveguides. Transmission line equivalent of a waveguide system. Impedance relation in waveguides. Waveguide impedance. Impedance matching in waveguides. Figure 5.19, examples of obstacles used in waveguide to introduce reflection together with equivalent transmission line systems. Impedance matching with resistive loads. Non-reflecting loads. Waveguide behavior at wavelengths greater than cutoff. Miscellaneous aspects and properties of waveguides. Coupling between coaxial lines and waveguides. Waveguide directional couplers. Magic T. This is the Magic T. Yeah. The waveguide arrangement illustrated in Figure 527A, termed a Magic T, possesses many of the qualities of a bridge. Thus, if the two side outlets C and D have the same length and are terminated identically, then the power delivered to the system at A divides at the junction and flows equally to C and D, with no output whatsoever being obtained at B. There you go. The resonant obstacles in waveguides. Comparison of waveguides and coaxial transmission lines. Cavity resonators. Any space enclosed by conducting walls possesses a resonant frequency for each particular type of field configuration that can exist in the space. Resonators of this type, commonly called cavity resonators, find extensive use as resonant circuits at extremely high frequencies. Figure 529, examples of cavity resonators. All these resonators except the prism are shown as cross-sections of figures of revolution. The field combinations shown for certain of the resonators correspond to the distributions with the dominant mode of operation. Figure 530, transition from concentric line to cylindrical cavity, showing electric fields for various intermediate or hybrid cases. A cavity resonator possesses many more modes than does the corresponding waveguide. For example, in the rectangular prism of Figure 529C, there are an infinite number of TE10N modes for each of the three axes of the prism. Thus, a triple infinity of modes exists in the rectangular prism corresponding to the single infinity of TEN0 waveguide modes. As a result, at frequencies appreciably greater than that corresponding to resonance at the dominant mode, it is found that the resonant frequencies of cavities will be extremely closely spaced. Q of cavity resonators. Resonant frequency of cavity resonators. Table 5.4. Properties of typical cavity resonators when operating in the dominant mode. And Table 5.3. Properties of cavity resonators for dominant mode. Coupling to cavity resonators. Figure 531, loop and probe coupling to cavity resonator. Problems and exercises. Chapter 6, fundamental properties of electron tubes. Electron tubes, devices that utilize the flow of free electrons in a vacuum or a partial vacuum are referred to as electron tubes. Such tubes are used to generate the radio frequency power required by radio and radar transmitters to control the energy thus generated, to amplify the weak radio frequency signals present at the receiver, to rectify or detect the signal, to amplify this rectified signal, and so on. The electron tube has made possible the long-distance telephone, talking pictures, public address systems, modern broadcasting, television, high-frequency and microwave radio, radar, guided missiles, etc. Altogether, it may be said that the electron tube is one of the most important devices that has resulted from modern science. There you go. Electrons, ions, and their motions. Free electrons and ions. Motions of electrons and ions in an electrostatic field. Effect of a magnetic field on a moving electron. Effect of combined electric and magnetic fields on electrons. Thermionic emission of electrons. Practical emitters. Practical emitting structures. Velocity of emission. Secondary emission. Both metals and insulators will emit secondary electrons when bombarded by electrons. The number of secondary electrons emitted per primary electron depends upon the velocity of the primary bombarding electrons and upon the nature and condition of the material composing the surface being bombarded. Potential assumed by an insulated secondary emitting target bombarded by an electron beam. Diodes, space charge effects. Voltage and current relations. Of course, a diode was originally a vacuum tube, wasn't it? Now it's made out of silicon. Does the same thing. Voltage and current relations in triode tubes. This is triodes, the control grid. Figure 6.9, relationship between grid voltage and plate current for several values of plate voltage in a typical triode tube. Note that the principal effect of changing the plate voltage is to displace the curves along the grid voltage axis without changing their shape. Figure 6.10, relationship between the plate voltage and plate current for several values of grid voltage for the same tube as in figure 6.9. Note that the principal effect of changing the grid voltage is to displace the curves along the plate voltage axis without changing the shape, and that the curves have the same general shape as those of figure 6.9. We've got grid current, coefficients of triode tubes, amplification factor. This is table 6.1, typical small vacuum tubes. Plate resistance. It is important to remember that the plate resistance is not the ratio of total plate voltage to total plate current. Transconductance or mutual conductance. Pentodes. A pentode is a 5-electrode tube consisting of cathode, plate, and 3 grids, which are concentrically arranged between cathode and plate, as in figure 6.14. There it is. Figure 6.14, schematic diagram of typical pentode tube showing electrode arrangement that provides effective electrostatic shielding between control grid and plate electrodes and their connecting leads. The result is that the number of electrons drawn from the space charge is substantially independent of the plate voltage. Figure 6.15, schematic representation of potential distribution in a pentode tube when a virtual cathode is present in the suppressor region. Figure 6.17, curves showing plate and screen current and total space current of a pentode as a function of plate voltage for various control grid potentials. Note that when the plate potential is too low, plate voltage has relatively little effect on the currents. Practical pentodes. Commercial pentode tubes are available from subminiature types up to tubes capable of developing 1 or 2 kilowatts of output. The most important use of pentodes is in audio frequency and tuned radio frequency voltage amplifiers. In addition, they are extensively used for the development of audio frequency power for radio receivers and small public address systems. Screen grid tetrode tubes. Figure 619, characteristic curve of a typical variable mu tube compared with the corresponding characteristic curve of a sharp cutoff tube. Voltage and current relations in screen grid tubes. Practical screen grid tubes. Historically, screen grid tubes came after the triode tube was developed and before practical pentode tubes were available. Screen grid tubes at present have limited practical application, however, because of the undesirable effects that result from the interchange of secondary electrons between plate and screen. In particular, the practical operating region, corresponding to a plate current that is substantially independent of plate voltage, is limited to the screen grid tube to plate potentials greater than the screen voltage. In contrast, the useful operating range of pentodes and beam tubes extends to much lower values of plate voltage. Beam tubes, we've got beam tubes. Coefficients of pentodes, screen grid, and beam tubes. Mu factor, the amplification factor of pentode, beam, and screen grid tubes. Relation between coefficients of pentode and similar tubes and triode coefficients. Mathematical representation of characteristic curves of tubes. Residual gas and its effects on the characteristics of high vacuum tubes. Effect of positive ion bombardment on cathodes. Evacuation of tubes, getters. Grid current due to ions, maximum permissible grid resistance. Special connections for conventional tubes. Transit time effects in diodes, triodes, and pentode tubes. Figure 628, diagram illustrating flux lines associated with an electron in successive stages of flight between cathode and plate, showing how the charge induced on the plate increases as the electron approaches the plate. Transit time effects in diodes, small signal case. Transit time effects in diodes, large signal condition. Transit time effects in triode and pentode tubes. Tubes for very high frequencies. Tubes intended for operation at extremely high radio frequencies must have small transit time in order to minimize grid loss, as discussed above. It is also necessary that both the inductance of the leads and the capacitance between electrodes be as small as possible. This is because at very high frequencies, such reactances become very important circuit elements. Finally, tubes intended for operation at the highest frequencies should have lead arrangements that make them suitable for use with resonant lines, coaxial or two-wire, as the case may be, or resonant cavities, since these are the resonant systems commonly used at very high radio frequencies. Hot cathode gas tubes, we've got gas diodes. Figure 636, current voltage characteristic of a typical gas diode. Yeah, there we go. Do they still call it the forward voltage? All right. Grid-controlled gas triodes, thyrotrons. Problems and exercises. Wow, 73 exercises. With a given plate voltage, the grid bias required to prevent conduction from taking place is a more negative voltage for grid-controlled gas triodes in the upper part of figure 638 than for electrode structure in the lower part of this figure. Explain. Chapter 7, Electron Optics and Cathode Ray Tubes. Electron optics, electrostatic lenses, focusing action of electrostatic fields, examples of electron lens systems, focusing action in triode and beam tubes, aberrations, magnetic lenses, magnetic lenses using longitudinal field, electron beams of uniform cross-section and high current density, the Pierce gun, control of mutual repulsion effects, fundamental features of cathode ray tubes, the electron gun, deflection systems, Figure 717, schematic illustration of a cathode ray tube with radial reflecting electrode, together with the typical screen pattern such as would result from using the deflecting plates to produce a circular trace while applying a synchronized pulse to the radial electrode. Cathode ray tube special considerations, transit time effects with electrostatic deflection, ion spot, burning and ion trap. Thermionic cathodes emit a small number of negative ions which, if allowed to strike the same part of the fluorescent screen over long periods of time, produce a darkening of the screen, termed burning. These ions follow the same path through the electrostatic focusing and deflecting fields of a cathode ray tube as do electrons, but having very low velocity, they are substantially unaffected by magnetic field used for either focusing or deflecting. Ions are particularly troublesome in cathode ray tubes employing electrostatic focusing and magnetic deflection. Here, the focusing system concentrates the ions into a sharply defined beam, while the fact that the magnetic deflection field has negligible effect upon the ions causes the ions always to strike the same spot on the screen. The result then is that as the tube is used, a dark spot gradually appears at a point on the screen corresponding to zero deflection. This ion blemish can be prevented by the use of a trap that removes the ions without affecting the electrons. While many forms of traps are possible, the most commonly employed arrangement is illustrated in figure 721. Have a look at that. Schematic diagram of ion trap. There you go. Photography of cathode ray traces. Problems and exercises. Chapter 8, Voltage amplifiers for audio frequencies. Vacuum tube amplifiers. Basic circuit of vacuum tube amplifier. Voltage and current relations in an amplifier tube. Methods of classifying amplifiers. Amplifiers are also designated as Class A, Class AB, Class B, Class C, or linear amplifiers according to the operating conditions. The term Class A is applied to an amplifier adjusted so that the plate voltage flows continuously throughout the cycle of the applied signal voltage. The subscript 1 is sometimes used to indicate that no grid current flows, while subscript 2 can be used to denote that the grid is driven positive at some part of the cycle of applied voltage. Thus, Class A2 amplifier is one in which the grid current does flow. In the Class B and linear amplifiers, the tube is biased approximately to cutoff so that the plate current in an individual tube flows in pulses lasting approximately a half cycle, while the Class C amplifier is adjusted so the plate current flows in pulses that last less than half a cycle. The Class AB is intermediate between the Class A and Class B adjustments. Distortion in amplifiers, phase distortion and time delay, equivalent circuit of the vacuum tube amplifier. According to this circuit equivalent, the effect on the plate current of applying a signal voltage EG to the grid is exactly as though the plate cathode circuit of the tube were a generator developing a voltage, mu EA, is that A? I'm not sure, and having an internal resistance equal to the plate resistance RP of the tube. Resistance, there's a little bit of plastic in here. Where that came from? Resistance coupled amplifiers. Variation of amplification with frequency when screen and cathode bypassing are fully effective. Figure 8.5. Circuit of resistance coupled amplifier employing a pento tube together with equivalent plate circuits useful in making amplifier calculations. Screen and bias bypass capacitors are assumed to have negligible effect. Universal amplification curve of resistance coupled amplifier. Resistance coupled amplifiers with incomplete screen and bias bypassing. Effective screen impedance. Effective bias impedance. Design of resistance coupled amplifiers. Figure 8.12. Curves giving the reduction in magnitude and the added phase shift of output voltage occurring at low frequencies in a resistance coupled amplifier as a result of resistance capacitor bias impedance RKCK for various values of RKGM for the case where the screen circuit impedance has negligible effect on the amplification. Resistance coupled amplifiers using triode tubes. Figure 8.13, characteristics of 6SJ7 tube. Transformer coupled voltage amplifiers and input transformers. Analysis of transformer coupled amplifiers. Figure 8.16, universal amplification curve of transformer coupled amplifier, giving the relative amplification and the phase shift characteristics. Transformer and tube characteristics. Direct coupled amplifiers. Drift in DC amplifiers. Direct coupled, not direct. Current. Tubes for DC amplifiers. Chapter 9, voltage amplifiers for video frequencies. Radio frequency, wideband voltage amplifiers. Responsive video amplifiers to pulses. Tubes for video voltage amplification, the gain bandwidth concept. High frequency compensation of video amplifiers, shunt peaking and other two-terminal compensating systems. Figure 9.6, examples of four-terminal compensating networks. Effects produced on the high-frequency response by cascading video amplifier stages. Practical construction of high-frequency compensating networks. General summarizing comments on high-frequency characteristics of video amplifiers. Table 9.2, comparative transient performance of different high-frequency compensating arrangements. Low-frequency defects of video amplifiers. Analysis of the low-frequency performance of video amplifiers in terms of transient behavior. Practical considerations relating to transient behavior at low frequencies. Analysis of low-frequency performance of video amplifiers in terms of amplification and phase characteristics. Compensation for low-frequency deficiencies in video amplifiers. Design considerations. Figure 9.15, typical SAG characteristics of compensated amplifiers under conditions where perfect compensation is not possible with the simple R1C1 network. Distributed amplifiers. Figure 9.19, a bridge T, artificial line sections suitable for use in practical distributed amplifiers. Although the sections are shown as being used in the grid line, they may be also employed in the plate line. Problems and exercises. Chapter 10, amplifier distortion, power amplifiers, and amplifier systems. Causes of amplitude distortion in amplifiers. Graphic method of determining amplifier wave shapes and distortion with resistance loads. Dynamic characteristic. Table 10.1. Doesn't say what it is. Voltages may be used in place of currents in these formulas if desired. Quantitative equations of distortion from load lines. Evaluation of wave shape distortion resulting from grid current. Mathematical analysis of amplitude distortion and cross-modulation in amplifiers. Power series analysis of amplifier behavior. Generalized equivalent circuit of vacuum tube amplifier. Analysis of distortion in typical cases. Resistance coupled and voltage amplifiers designed for large output voltages. Class A power amplifiers. Plate efficiency. Basic power relations. Distortion in Class A power amplifiers. Tubes for Class A power amplification. Triode, beam, and pentode tubes all find use as Class A power amplifiers. Triodes have the advantage of less distortion, but generally give lower plate efficiency and require a greater driving voltage than do beam and pentode tubes. Selection of operating condition and load resistances for Class A amplifiers. Output transformers in Class A amplifiers. Figure 10.12, equivalent circuits for triode power amplifier using output transformer. Analysis of the frequency response characteristics, triode case. It will be observed that the output voltage falls off to 70.7% of its mid-frequency range value when the frequency is such that the reactance of the primary incremental inductance equals the resistance R formed by the effective plate resistance R prime P in parallel with the effective load resistance capital R prime L. It will be observed that the output voltage at high frequency falls to 70.7% of its value in the middle range of frequencies when the frequency is such that the reactance of the leakage inductance is equal to the resistance capital R prime formed by the effective plate resistance lowercase r prime P and the effective load resistance capital R prime L in series. Analysis of the frequency response characteristics, pentode and beam tube case. Transformation ratio and transformer efficiency. Measurement of transformer characteristics. Power rating of output transformers. Push-pull Class A amplifiers. Exciting systems for push-pull amplifiers. Class B and Class AB power amplifiers. Analysis of Class B operation. Discussion of operating features of Class B amplifiers. Class AB amplifiers. Cathode follower amplifiers. Analysis of cathode follower circuit. Operating characteristics of cathode follower amplifiers. Regeneration in multi-stage audio and video frequency amplifiers. Regeneration at low frequency, motorboating. The most troublesome form of regeneration in audio and video frequency amplifiers occurs when several stages of amplification operate from a common source of plate power, as shown in figure 1026A. Here, amplified current IP, in flowing through the source impedance ZS, develops a voltage EFB across the output terminals AA of the power supply. Pardon me. Which acts directly in the plate circuits of all of the stages. This corresponds to a form of feedback analogous to the feedback discussed in Chapter 11. Just going to take a quick break. All right, on we go. High frequency regeneration, volume control in audio and video frequency amplifiers, automatic volume control, volume expansion and contraction, hum and microphone effects in audio and video amplifiers. The term hum refers to alternating voltages appearing in the output of an amplifier as a result of the effect of power frequency, voltages, currents, and fields. In audio and video frequency amplifiers, hum results from the introduction into the amplifier circuits of currents of the power frequency and its harmonics, which are amplified directly by the amplifier. Such hum is particularly troublesome in high-gain systems, since then effects introduced in low-level stages are subjected to large amounts of amplification. The possible sources of hum are stray magnetic fields, stray electrostatic fields, alternating currents in the heaters or filaments of the tubes, and incompletely filtered power supply systems. The problem of avoiding hum while using alternating current to heat the cathodes of the amplifier tubes is discussed in section 20-1 that is, and can be handled by a suitable choice of tubes. Hum from the power supply system is a design problem, the solution of which presents no particular difficulty. The hum that is most difficult to handle arises from stray magnetic and electrostatic fields. Magnetic fields induce voltages in coils or in loops that can exist if the wiring is improperly arranged and may even affect the flow of electrons between the cathode and the plate of a tube. The principal sources of magnetic fields in the vicinity of an amplifier are the power transformer and the leads carrying the filament or heated currents of the tubes. Such leads should hence be arranged in the form of a twisted pair to minimize their magnetic effects. Power transformers should be placed as far as possible from portions of the system sensitive to magnetic fields, particularly input transformers and associated tubes. The stray magnetic field can be minimized by designing the power transformer to have low leakage flux, achieved by using low flux densities and the smallest possible air gap in the core. It is also helpful to employ a non-magnetic chassis, or at least to isolate the input and power transformers from a sheet iron chassis by mounting either or both upon a non-magnetic base that is then fastened to the chassis. Input transformers present a particularly difficult problem in high-gain audio frequency amplifiers because they operate at the point in the system where the power level is lowest. The input transformer of a high-gain audio frequency amplifier must be magnetically shielded and should be placed as far as possible from the power transformer with an orientation that experiment indicates will minimize hum pickup. In many cases, the input transformer and one or two stages of resistance-coupled amplification are built in a separate unit termed a preamplifier, which can be located some distance from the main amplifier chassis and transformer and is energized through cables. Lines connecting the microphone or other source of power to an input transformer and lines connecting the output of the preamplifier system to the main amplifier should preferably be of low impedance, that is 600 ohms or less, and should consist of a twisted pair of wires electrostatically shielded. The input transformer should always be provided with an electrostatic shield between primary and secondary. Microphone effects. When a tube is jarred, the electrodes tend to vibrate mechanically, giving rise to effects characterized by the term microphonic action. Thus, vibrations cause changes in the plate current, which are usually in the audible frequency range and which are, therefore, amplified in audio and video frequency amplifiers. And we're off problems and exercises. Chapter 11, Negative Feedback in Amplifiers. Feedback amplifiers, fundamental considerations relating to amplification and distortion. Effect of negative feedback on voltage amplification. Expressed in words, equation 11.3 states that when the feedback factor alpha beta is large, the effective amplification depends only upon the fraction beta of the output voltage and is superimposed upon the amplifier circuit and is substantially independent of the gain A actually produced by the amplifier itself. Effect of negative feedback on distortion and hum. The presence of negative feedback also greatly reduces the amplitude distortion appearing at the output terminals of an amplifier. Conditions for avoiding oscillation in feedback amplifiers. Design of feedback systems as influenced by oscillation considerations. Relation of phase shift to transmission characteristics. Figure 11.4. Examples of the relationship that exists between phase shift and the variation in transmission. Idealized feedback characteristics. The relation that exists between phase shift and variation in amplitude of transmission makes it possible to formulate a general method of designing feedback amplifiers that will ensure the absence of oscillations. This involves appropriately shaping the curve, giving the magnitude of alpha beta as a function of frequency. It is not necessary to pay any attention to the phase shift of alpha beta in carrying out the design, since the phase shift of alpha beta is determined by the amplitude variations of alpha beta. It is therefore possible to guarantee that the phase shift will be less than 180 degrees at all frequencies for which the absolute value of alpha beta is much greater than 1, merely by properly controlling the variation of the absolute value of alpha and beta with frequency. Figure 11.6, ideal characteristic of figure 11.5 for k equals 1.0, together with the characteristic of an actual two-stage resistance coupled amplifier that is free of screen and bias impedance effects. Practical form of ideal feedback characteristic. Asymptotic slope of amplifiers. Frequency range over which control of the absolute value of alpha beta is required. Practical application of design principles. Figure 11.8. Example of an amplifier designed to provide 30 decibel of useful feedback with margins of safety for amplitude and phase of 10 decibels and 36 degrees, respectively. Feedback amplifiers, miscellaneous aspects, practical circuit arrangements for producing negative feedback. Figure 11.13, typical feedback circuits involving 3 stages of amplification. Voltage feedback and current feedback. Effect of negative feedback on effective output impedance of amplifiers. Practical use of the feedback principles in amplifiers. Servo mechanisms. Figure 11.15, schematic diagrams of servo mechanism showing basic elements and a particular example. And problems and exercises. Tuned voltage amplifiers. The single tuned amplifier, direct coupling. Transformer or inductive coupling. Complex coupling. Figure 12.4, variation of equivalent mutual inductance with frequency in typical complex coupling systems. Multi-stage single-tune amplifiers. Table 12.1, relative values of half-power bandwidth of multi-stage tune amplifier composed of identical stages. The double-tuned amplifier. Figure 12.6, actual and equivalent circuits of a double-tuned amplifier. And figure 12.7, the effective coefficient of coupling upon the shape of the amplification curve of a double-tuned amplifier. Miscellaneous aspect of tune amplifiers. Off-channel selectivity. Phase and time delay characteristics of tuned amplifiers. Envelope delay. Amplitude distortion and crosstalk in tuned amplifiers. Voltage control in tuned amplifiers. Wideband tune amplifiers. Transient response of tuned amplifiers. Single tune wideband amplifiers. The gain bandwidth concept with special reference to single tune stages and tubes for wideband tuned amplifiers. Double tuned wideband amplifiers. Comparison of double tune and single tune wideband amplifiers. Stagger-tuned amplifiers, basic relationships in stagger-tuned pair, and comparison with single-tune and double-tune systems. Staggered systems of higher order. Regeneration in multi-stage tuned amplifiers. Control of regeneration. Figure 12.14, methods of locating ground connections in a multi-stage tuned amplifier to minimize common couplings introduced by the chassis, together with decoupling filters RC for isolating individual stages. Input admittance and of triode amplifiers. Analysis of input admittance of triodes. Practical importance of the input admittance of triode in audio and video amplifiers. Neutralization of input admittance of vacuum tube amplifiers, grounded grid systems. Figure 12.18, equivalent bridge circuits of neutralized amplifiers of figure 12.17a and c. Grounded grid circuits. Figure 12.19, circuit of grounded grid amplifier together with equivalent plate and input circuits. Input admittance of pentode, beam, and screen grid tubes. Input capacitance. Input capacitance of pentodes and similar tubes. Circuit and tube noise. Resistance noise. Tube noise. Shot effect noise in diodes. The anode current of a diode contains a noise component as a result of random variations in the rate of emission of electrons from the cathode. When the current flow is limited by the cathode temperature, that is, when all electrons emitted are attracted to the anode, the noise component of the anode current, that is, the shot effect noise, is given as this. Okay. When the anode current of a diode is limited by space charge, the consequences of irregularities in emission are greatly smoothed out, and the noise component of the plate current becomes only a small fraction of the noise associated with the same plate current under temperature-limited conditions. This smoothing action arises from the fact that a random increase in emission instantaneously increases the negative space charge. This in turn causes some electrons that would otherwise just barely be able to go to the plate to return to the cathode instead, thus minimizing the consequences of the increase in emission. Triode noise. Induced input circuit noise. Signal to noise ratio and noise figure. Signal to noise of an ideal system. Equivalent noise bandwidth of an amplifier. Problems and exercises. Chapter 13, tuned power amplifiers. Class C tuned amplifiers. Voltage, current, and impedance relations in Class C amplifiers. Power and efficiency. Figure 13.1, voltage, current, and power relations in a typical Class C amplifier. Factors involved in the operation of Class C amplifiers with particular reference to triode tubes. Class C amplifiers employing beam, pentode, and screen grid tubes. Tubes suitable for Class C amplifiers. Circuit arrangements and considerations in Class C amplifiers. Table 13.1, characteristics of representative Class C amplifier tubes. Table 13.1 continued. Okay, so it's the same table again with more data. Considerations relating to the plate tank circuit. Class C amplifier calculations and design. Calculation of triode Class C amplifier performance. Design considerations in triode Class C amplifiers. Practical adjustment of triode Class C amplifiers. Special considerations involved in Class C amplifiers using beam, tetrode, and similar tubes. Figure 13.12. Effect of different values of EL on the voltage, current, and power relations of typical Class C amplifier employing a beam tube. It is to be observed that in many of the oscillograms, the solid and dash curves coincide. Note the similarity of the solid curves to the oscillograms of figure 13.1. Calculation of performance. Experimental adjustment. Comparison of triodes with beam and similar tubes as Class C amplifiers. Harmonic generators. Factors governing harmonic generator performance. Design and analysis of harmonic generator performance. Class C amplifier. Oh, okay. Linear or tuned Class B amplifiers. Efficiency and power. Figure 13.15. Typical linearity or saturation curves of linear amplifier for different load impedances introduced between the plate and cathode by the plate tank circuit. Linear amplification of wideband signals. Special considerations involved in the operation of Class C and similar amplifiers at ultra-high frequencies. Transit time effects. Circuits for ultra-high frequency Class C and similar power amplifiers. Tubes and tube performance at ultra-high frequency. Chapter 14. Vacuum tube oscillators. Oscillator circuit arrangements. Figure 14.1. Schematic circuits of common types of power oscillators. To simplify the circuit diagrams, the methods of introducing the plate supply voltage and of developing the grid bias are not shown. Amplitude of oscillations, amplitude limiting, Class A and Class C oscillators, intermittent operation of oscillators employing grid leak bias, noise modulation in oscillators, design and adjustment of power oscillators, frequency and frequency stability of oscillators, factors contributing to high stability frequency, oscillators with oscillators with multiply resonant circuits. I don't know if that's grammatical, I'm not sure. Synchronization of vacuum tube oscillators, electron coupled oscillators. Figure 14.3, electron coupled oscillator circuits. Oscillators for very high frequency. Resonant line arrangements. Butterfly oscillators. Holes and discontinuities in high frequency oscillators having a wide tuning range. Oscillators with resistance capacitance tuning, RC oscillators. Negative resistance oscillators. Parasitic oscillations. Examples of parasitic oscillations. Figure 14.14. Some actual amplifier circuits and the equivalent circuits involved in high-frequency parasitic oscillation. Figure 14.15. Amplifier circuit with radio frequency chokes, together with low-frequency parasitic circuit that can exist as a result of these chokes. Piezoelectric quartz crystals. Piezoelectricity. Equivalent electrical circuit of vibrating quartz crystal. Table 14.1. Characteristics of a typical quartz crystal. Crystal activity. Crystal electrodes and mounting. Resonant frequencies in crystals. Vibrational modes and actual equivalent electrical circuit. Temperature coefficient of resonant frequency. Table 14.2. Typical crystal cuts with low temperature coefficients. Variation of resonant frequency with time, aging. Crystal oscillator circuits. Pierce circuit. Bridge stabilized oscillator circuit. Power output and frequency stability of crystal oscillators. Problems and exercises. Chapter 15. Amplitude modulation. Waves with amplitude modulation. Analysis of amplitude modulated waves. Table 15.1. Modulation frequencies corresponding to typical signals. Distortion in amplitude modulated waves. Plate modulated Class C amplifiers. Plate modulated Class C amplifiers employing triode tubes. Figure 15.2. Circuit diagrams of typical plate modulated Class C amplifiers. For the sake of simplicity, the neutralizing arrangement for the triode case is omitted. Figure 15.3. Oscillograms illustrating the operation of plate modulated Class C amplifier with fixed bias and with grid leak bias. Special considerations in plate modulated Class C amplifiers employing beam or tetrode tubes. Power requirements of the modulator. Grid modulated Class C amplifiers. Figure 15.5. Circuit of tetrode grid modulated Class C amplifier together with oscillograms showing details of operation. Figure 15.6. Relationship between output voltage and modulating voltage in a typical grid modulated amplifier. Miscellaneous systems of modulation. Suppressor grid modulated Class C amplifier. Screen grid modulated Class C amplifiers. Figure 15.7. Circuit of suppressor grid modulated amplifier together with curves showing typical relationship between output voltage and suppressor grid voltage. Figure 15.8. Schematic circuit of a screen grid modulated Class C amplifier. Modulated Class A amplifier. Figure 15.9. Circuit of modulated Class A amplifier together with oscillograms showing details of operation. Plate modulated oscillator. Modulations by mean of nonlinear circuit elements. Carrier suppression, single sideband and vestigial sideband systems. Pardon me, I was going to take a quick break. Alright, I'm back. So this is carrier suppression, single sideband and vestigial sideband systems. I already read that bit, didn't I? All right. Carrier suppression by means of balanced modulators. Single sideband generation. Vestigial sideband systems. Under some circumstances, it is desirable to obtain a wave consisting of a carrier plus one sideband with the other sideband suppressed. Such a result can be approximated by transmitting an ordinary amplitude module wave through a filter that is so designed that the edge of the transmission band of the filter accurately coincides with the carrier frequency, as shown in figure 15/16b. The resulting wave then has the frequency spectrum illustrated in 15/16c, which is characterized by a residual second sideband. This is termed a vestigial or asymmetric sideband system and has the advantage of requiring less total bandwidth than does the amplitude modulated wave with its two full sidebands. In the standard type of signal used in the television, it is the standard type of signal used in television transmitters. Problems and exercises. Chapter 16, detectors and mixers. Detection of amplitude modulated waves. Diode detectors. Practical diode detectors. Amplitude frequency and phase distortion in practical diode detectors. Performance of practical diode detectors. Plate detectors. Class A detector and squared law action. Vacuum tube detectors as vacuum tube voltmeters. Plate detection types. Figure 16.8, a schematic diagram of diode type vacuum tube voltmeter provided with DC amplifier. Waveform effects in vacuum tube voltmeters. Crystal diode voltmeters. The use of rotating vectors to determine envelope properties and phase variations of modulated waves. Behavior of detectors when the applied signal consists of two amplitude modulated waves. Supergenerative detectors. Frequency translation. Analysis of heterodyne action resulting from superimposing two waves of different frequencies. Mixer and converter tubes for frequency translation. Quantitative analysis of mixer tube operation, conversion, transconductance. Quantitative analysis. Harmonic and some frequency operation of mixers. Noise in mixer tubes. Relative merits of different mixer types with respect to noise. Crystal diode mixers. Practical operating considerations, conversion loss and noise temperature. Problems and exercises. Chapter 17, frequency modulation. Frequency modulated waves. Analysis of frequency modulated waves. A fundamental characteristic of a frequency modulated wave is that the frequency deviation delta F is proportional to the peak amplitude of the modulating signal and is independent of the modulating frequency. Effect of frequency multiplication, frequency division, and frequency translation upon frequency modulated waves. Phase modulation. A phase-modulated wave is a sine wave, such as represented by equation 17.3, in which the value of the reference phase theta is varied so that its magnitude is proportional to the instantaneous amplitude of the modulating signal. Relation of frequency and phase-modulated waves to amplitude-modulated waves. Responsive networks to frequency-modulated waves. Production of frequency and phase-modulated waves. Frequency-modulated oscillator using reactance tube modulator. Phase modulators. Phase modulators are important in frequency modulation work because, as pointed out above, a frequency modulated wave is obtained when the modulating voltage applied to a phase modulator is inversely proportional to the modulating frequency. Many systems for producing phase modulation have been devised, each of which can be used to produce either phase or frequency modulated waves. Several of the more frequently used and representative of these will now be described. Space limitations prevent all of the types of phase modulators in common use from being described in these pages. An additional system of importance generates a phase shift by varying the instant during the cycle when a pulse is generated. Phase modulators of this type are capable of producing a modulation index approaching 2.0. An example of such a system is given by James F. Gordon, a new angular velocity modulation system employing pulse techniques, proceedings of IRE Vol 34, blah, blah, blah. Again, a special tube called the phasitron has been devised, which varies the phase angle by control of an electron stream. This tube, which is capable of producing a modulation index of 6.0, is described in another paper. Detection of frequency and phase modulated waves. The phase shift discriminator. Figure 17.14. Frequency modulation detector employing phase shift discriminator. Frequency modulation detectors using the phase shift discriminator. Figure 17.15, practical form of phase shift discriminator of figure 17.14a. The ratio detector. Suppression of response to amplitude modulation occurring simultaneously with frequency modulation. Practical ratio detector circuits. Problems and exercises. Chapter 18, Wave Shaping, Nonlinear Waves and Pulse Techniques. Non-sinusoidal wave shapes. Clipping. In clipping, a portion of a wave is flattened off or limited to some arbitrary level, irrespective of the amplitude of the original signal. Clippers may be conveniently classified as peak clippers, base clippers, and slicers, according to the way in which they operate on a wave. There you go. Integration and differentiation of waveforms. Integration and differentiation with the aid of operational amplifiers. That's why they're called operational amplifiers, because they can do things like differentiation and integration. The multivibrator. The multivibrator can be thought of as a two-stage resistance-coupled amplifier in which the voltage developed by the output of the second tube is applied to the input of the first tube. A schematic diagram of the plate-coupled form of multivibrator is shown in Figure 18-9A. Such an arrangement will oscillate because each tube produces a phase shift of 180 degrees, thereby causing the output of the second tube to supply to the first tube an input voltage that has exactly the right phase to sustain oscillations. The usefulness of the multivibrator arises because 1. The multivibrator can be used as a generator of square waves, pulses, or time intervals. 2. The frequency of oscillation is readily controlled by an injected voltage. And 3. The wave that is generated is very rich in harmonics. Frequency of multivibrator oscillation. Synchronizing the multivibrator. One-shot monostable multivibrators. The flip-flop Eccles-Jordan circuit. That didn't stick around, did it? The Eccles-Jordan circuit. We just call it a flip-flop still. The blocking oscillator. Pulse length and shape. One-shot operation of the blocking oscillator. Practical applications of the blocking oscillator. Square wave generation. Pulse generators. Pulse generation by differentiation. Pulse generation by use of the multivibrator. Pulse generation by use of the blocking oscillator. Lines and pulse-forming networks in pulse generation. Line pulses. Lines and switches. Delay line control of pulse length in the multivibrator and blocking oscillator. Clamping circuits, DC restoration. Diode and grid clamps. Keyed clamps. Sawtooth wave generators. Sawtooth generators using high vacuum tubes. Figure 1837. Sawtooth wave generators employing high vacuum triodes together with typical waveforms. Linearization refinements in sawtooth wave generators. Constant current capacitor charging by use of a pentode. Bootstrap circuit. Sawtooth wave generators based on the Miller integrator. Production of sawtooth wave of current in an inductance resistance circuit. Time delay circuits. Circuit requirements imposed by nonlinear waveforms, pulse transformers. Pulse transformers. Miscellaneous types of special circuit arrangements. Coincidence amplifier. Counting and scaling circuits. Frequency division. Summing amplifier. It is sometimes desired to obtain a wave that is the sum of two or more individual waves. One method of achieving this result consists in applying each wave to the control grid of a separate pentode amplifier tube, while connecting in parallel the plates of all the tubes involved and providing a single plate load impedance for the combination. Problems and exercises. Not problems and amplifiers. Dear me. All right. Chapter 19, microwave tubes. Microwave tubes. The limitations of triode, pentode, and similar tubes that arise at very high frequencies as a result of transit time effects can be avoided by employing types of tubes which make use of transit time in achieving their normal operation. The most important tubes in this category are the multi-cavity and reflex klystrons, the traveling wave tube, the backward wave oscillator, and the magnetron. Such tubes are particularly suitable for use in the microwave frequency range and have made possible the practical development of these higher frequencies. Multi-cavity klystron amplifier, mechanism of klystron operation, velocity modulation, and current modulation. Performance and application of multi-cavity klystron amplifier, the reflex klystron oscillator, electronic admittance of the gap, operating characteristics of reflex klystron oscillators, frequency electronic tuning, the traveling wave tube. Figure 1912, schematic diagram of traveling wave tube. Mechanism of operation. Suppression of oscillations, helix attenuator. Bandwidth. Backward wave oscillators, the carcinotron. The backward wave oscillator, or the O-carcinotron, as it is sometimes called, is a development that has grown out of the traveling wave idea. However, in contrast with the traveling wave tube, it is inherently an oscillator. Mechanism of operation. Helix form of backward wave oscillator. Frequency of oscillation. Power and efficiency. Magnetron oscillators. Mechanism by which oscillations are generated. Performance of magnetrons. Automatic frequency control of microwave oscillators. Problems and exercises. Chapter 20. Power for operating vacuum tubes. AC hum from cathode heating power. AC hum in heater type tubes. Rectifiers for supplying anode power. High vacuum rectifier tubes. Hot cathode mercury vapor rectifier tubes. Table 21, characteristics of typical rectifier tubes. Rectifier circuits. Single phase rectifier circuits. Voltage multiplying circuits. Polyphase circuits. Behavior of rectifiers when used with filter systems having series inductance, choke input. Voltage and current relations in rectifier tubes with choke input filters. Input inductance requirements. Table 22, characteristics of typical rectifiers operated with inductance input filter systems. Voltage regulation in input inductance systems. Behavior of rectifiers when used with filter systems having shunt capacitor input. Analysis of capacitor input systems. Little blemish there. What that is? Some sort of stain. Comparison of capacitor input and inductance input systems. Filters. Voltage and current relations in filters. Figure 2012, typical filters. Graded filters. Filter inductances and capacitances. Example of rectifier filter calculations. Voltage regulated power supply systems. In many circumstances, it is desired to obtain an output voltage that will be substantially constant at some arbitrarily chosen value, irrespective of changes in AC supply voltage or the DC load current. The method ordinarily employed to achieve this result is shown schematically in Figure 2015. This is a feedback control system of the type discussed in Section 11.6. Here, a reference voltage ER is compared with a fraction gamma E0 of the output voltage obtained by an adjustable potentiometer P that is set at a point such that gamma E0 approximately equal the reference voltage ER when the output voltage has the desired value E0. Anode power for high voltage cathode ray tubes. Plate power from low voltage DC sources. Problems and exercises. Chapter 21, Transistors and Related Semiconductor Devices. Semiconductors. There's a note here, 2. Oh, there's heaps of notes. The whole chapter has a note. Number 1. The literature on semiconductors, with particular reference to transistors, is mostly of such recent origin and is growing so rapidly that no attempt is made to annotate this chapter beyond indicating the origin of some of the viewpoints and relations that are presented. The purpose of this treatment is to introduce the basic phenomena of semiconductors, and particularly of transistors, in simple words that give a clear and accurate semi-quantitative understanding of those devices. Okay, and then the second note says, the reader who desires to do some supplementary reading on the properties of semiconductors and transistor fundamentals can profitably start with the paper by W. Shockley, Transistor Electronics, Imperfections, Unipolar and Analog Transistors, Proceedings of the IRE, Volume 40, page 1289, November 1952. That's 3 years before this book was published. This entire issue of Proceedings of the IRE is devoted to transistors and contains much useful and readable information on the subject. And then the third note here says, for convenience, this discussion is largely developed in terms of germanium. However, it also applies with little change to silicon. This is because, like germanium, silicon is a tetravalent atom that crystallizes in the manner illustrated in Figure 21.1, which is from the Bell System Tech Journal, Volume 28, page 338, July 1949. The principal difference between silicon and germanium insofar as electrical properties are concerned, is that it takes more energy to break the covalent bonds in the crystallized silicon. As a result, the intrinsic conductivity of silicon is less than that of germanium. The effect of impurities on the conductivity is also slightly different in detail, although not in character. Okay. So, the term semiconductor denotes solid material having a conductivity considerably more than that of a good insulator and yet much less than that of a metal. In recent years, a number of devices based on semiconductors have been developed that are of great practical usefulness in electronics. Most important of these is the transistor, which is an amplifier having properties similar to those of a vacuum tube, but which requires no cathode power and at the same time offers the hope of practically unlimited life. Additionally, new types of rectifiers, improved photoconductive materials, etc., have also been developed. The discussion of semiconductors that is to follow emphasizes germanium and silicon. While many other semiconducting materials are known, they find much less practical use in electronics. Furthermore, the principles determining the electrical behavior of germanium and silicon also apply with little or no change to these other materials. Conductivity of pure intrinsic semiconductors. Crystal structure of germanium covalent bonds. Production of free electrons by thermal processes. Holes. Recombination of holes and electrons. Hole and electron density. Impurity semiconductors. Donor or N-type semiconductors. Acceptor or P-type semiconductors. Conductivity and carrier concentrations in impurity semiconductors. Mechanisms involved in current flow, drift and diffusion. Current flow produced in N-type material by an applied voltage. Current flow produced in P-type material by an applied voltage. Terminal electrode effects. Current flow by diffusion. Conductivity of insulators, metals, and semiconductors in terms of energy bands. Conductivity of insulators and semiconductors. Conductivity of metals. The junction diode. The energy barrier and the p-n junction. Carrier movement and current flow across unbiased junction. Carrier movement and current flow across a biased junction. Junction capacitance. Examination of figure 21.9a and d shows that on opposite sides of the p-n junction, there are regions containing immobile charges of opposite sign in close proximity to each other. This is the situation that exists in any capacitor. Since the capacitance of a capacitor depends on the spacing of the charges and is greater if the charges are close together, the capacitance of the p-n junction will change with the applied voltage. It diminishes with increased voltage in the reverse bias direction because, as seen from figure 21.10, the average separation of the uncovered charges is greater in C than in A. The fact that there is more total charge in C is of no consequence, for the capacitance of a condenser depends only upon the geometry of the situation, not upon the charge actually present. Unsymmetrical junctions. Further consideration of carrier drift and diffusion in biased p-n junctions. Carrier drift and diffusion with reverse bias. Diffusion length. Ratio of electron to hole current at the junction. Circuit properties of the p-n junction. Charge storage phenomenon. Complications arrive when it is desired to switch a diode as rapidly as possible from full conduction in the forward direction to full voltage with small current in the reverse direction. The junction triode transistor. Types of construction. Current flow, general character. Conventions on polarities and graphical symbols. look at this. We don't draw a transistor like that anymore. Fascinating. Figure 2116, carrier concentrations and current components in junction triode transistor. Oh, there we go. This is the EBC. There we go. That's the transistor notation that we're familiar with largely. Sometimes they put a circle around it, of course. Details of actions taking place in the junction triode transistor, carrier movement and current flow. Flow diagram of currents. Effect of collector voltage on the properties of the junction triode transistor. Ratio of collector to emit a current, transistor alpha. Small signal equations and equivalent circuits of the transistor, voltage and current equations. Table 21.1, characteristics of a typical junction transistor. Equivalent circuit derived from physical processes of transistor operation. High frequency effects in junction transistors. Alpha cutoff frequency and related transit time effects. Equivalent transistor circuits for high frequencies. Common emitter and common collector connections for transistors. Common emitter circuit. Common collector connection. Measurement of transistor characteristics. The H parameters appearing in equation 2125 and giving the small signal behavior of the transistor can be readily measured by direct use of equations 2126 to 2129. The necessary circuit arrangement are given in figure 2134. In all of these circuits, the emitter bias is supplied by an adjustable voltage through impedance RL that is high at the test oscillator frequency, compared with the input resistance of the emitter electrode, while the collector bias voltage is obtained from an adjustable voltage having an internal impedance low compared with the conductor resistance. Okay. Improved junction transistors for high frequencies. The PNIP junction triode transistor. A transistor structure offering great possibilities for improved high-frequency performance is the PNIP arrangement shown in figure 2136, or its counterpart, the NPIN structure. The principal features here are a base region which is very thin and which has high conductivity, is heavily doped, but which is separated from the collector by a relatively thick layer of intrinsic material. The effect of the intrinsic layer is equivalent to increasing greatly the thickness of the base collector transition region. This reduces the effective base collector barrier capacitance C, making it possible simultaneously to increase the base conductivity to the point where the base resistance R'B is very low even when the base is made very thin in order to achieve a high alpha cutoff frequency. An additional advantage of this arrangement is that it reduces the variation of base thickness with collector voltage. Hence, the output admittance Y'(C) and the voltage MV'(C) in figure 2126 can become almost negligible. The low conductivity of the intrinsic material in figure 2136 produces a large voltage drop across this layer and a substantial electric field within it. This is no particular disadvantage, however, since it can be compensated for by increasing the collector bias voltage correspondingly. Although the intrinsic material has low conductivity, the carriers from the base still cross it as a result of drift action induced by the electric field. Very few carriers are lost in the intrinsic material due to recombination because of the low concentration there of carriers of the opposite type. Point contact diodes, point contact transistor, Table 21.2, comparison of coefficients of typical point contact and junction transistors for equivalent circuit of figure 21.22. I don't think we see point contact transistors anymore, but junctions, the bipolar junction transistor is still with us. Transistor applications, small signal amplifiers. Input and output resistances and power gain of transistor amplifiers. Audio frequency power amplifiers. Transistor oscillators. Pulse circuits. Noise in transistors. Problems and exercises. Chapter 22, Propagation of Radio Waves. Factors involved in the propagation of radio waves. There are a number of mechanisms by which radio waves may travel from a transmitting to a receiving antenna. The more important of these are designated by the terms ground waves, sky waves, and space or tropospheric waves. Okay, the ground wave, also sometimes called a surface wave, can exist when the transmitting and receiving antennas are close to the surface of the Earth and are vertically polarized. The sky wave represents the energy that reaches the receiving antenna as a result of bending of the wave path introduced by the ionization in the upper atmosphere. And the space wave represents energy that travels from the transmitting to the receiving antenna in the Earth's troposphere. That is, the portion of the Earth's atmosphere in the first 10 miles adjacent to the Earth's surface. The space wave commonly consists of at least two components. One of these is a ray that travels directly from transmitter to receiver, while the other is a ray that reaches the receiver as a result of reflection from the surface of the Earth. Space wave energy may also reach the receiver as a result of reflection or refraction produced by variations in the electrical characteristics of the troposphere and by diffraction around the curvature of the Earth, hills, etc. Radio transmission at frequencies above about 30 megacycles, that is, at the frequencies used for television, frequency modulation, radar, etc., is normally space wave propagation. The ground wave. Earth constants. Reflection of radio waves by the surface of the Earth. Space wave propagation. Space wave propagation over ideal flat Earth. Miscellaneous considerations in space wave propagation. Effect of Earth imperfection and roughness on field strength in the interference zone. Interference zone. Shadowing effects of hills and buildings. Variation of field strength with height. Transition between ground and space waves. Comparison of vertical and horizontal polarization to space wave propagation. Atmospheric effects in space wave propagation. Refractive index of air. Refraction of rays and the radio horizon. Duct propagation. Extended range propagation resulting from tropospheric scattering and reflection. General picture of ionosphere and its effect on radio waves. The ionosphere and its layers. Layer characteristics. Mechanism by which the ionosphere affects radio wave propagation. Effect of the Earth's magnetic field. The effect that electrons in the atmosphere have on radio waves is influenced by the fact that these electrons are in the presence of the Earth's magnetic field, which exerts a deflecting force on the moving electrons, as explained in section 6.2. The force on each has a magnitude proportional to the product of instantaneous velocity of the electron and the component of the Earth's magnetic field that is at right angles to the velocity of the electron. The direction of the force is at right angles to the velocity of the electron and also at right angles to the component of the magnetic field giving rise to the force. At the higher radio frequencies, a component of magnetic field at right angles to the electric field of the incident radio wave causes the vibrating electrons to follow elliptical paths as illustrated in figure 2222A and B. Since certain portions of such paths have components at right angles to the electric field of the wave, some of the energy absorbed by the electrons from the wave is re-radiated with a polarization that is rotated 90 degrees in space with respect to the polarization of the incident wave. This re-radiated cross-polarized component also generally differs in time phase from the field of the incident wave. Hence, the Earth's magnetic field will normally cause a radio wave that was originally plane polarized to become elliptically polarized after it has traveled some distance in the ionosphere. As a note here, in some situations, 3 components are produced. Okay. Energy losses in the ionosphere. Refraction and reflection of sky waves by the ionosphere. The critical frequency. Reflection. Ray paths, skip distance, and maximum usable frequency. Multiple hop transmission. Vertical incident measurements of the ionosphere, group velocity and group delay. Interpretation of vertical incidence records. Relations between oblique and vertical incidence transmission. Transmission curves and their use to obtain skip distance and maximum usable frequency. Approximate lower ray behavior at oblique incidence. Skywave signal strength. Miscellaneous aspects of ionospheric propagation. Fading. Backscatter measurements, scatter sounding. Meteor ionization. Extended range propagation by forward scatter from the ionosphere. Propagation characteristics of radio waves of different frequencies in relation to the problems of practical radio communication. Propagation characteristics of radio waves in the frequency range 20 to 100 kilocycles. Propagation characteristics at broadcast frequencies. Propagation characteristics at short waves, 1600 kilocycles to 30 megacycles. Propagation of frequencies above 30 megacycles. Relation of solar activity to the propagation of radio waves. Ionospheric storms. Noise and static. Cosmic or galactic and solar noise. Precipitation static. Rayleigh-Carson reciprocity theorem. There are various reciprocal relations that relate the properties of waves traveling in one direction to the properties of wave traveling in the opposite direction, and similarly connect the properties possessed by an antenna when transmitting with the properties possessed in reception. These relations are incorporated in reciprocal theorems, the most important of which was formulated by Rayleigh and extended to include radio communication by John Carson. It is to the effect that if an electromotive force E inserted in antenna 1 causes a current I to flow at a certain point in the second antenna 2, then the voltage E applied at this point in the second antenna will produce the same current I, both in magnitude and phase, in a short circuit at the point in antenna 1 where the voltage E was originally applied. The Rayleigh-Carson theorem fails to be true only when the propagation of the radio waves is appreciably affected by the presence of the Earth's magnetic field. It thus holds for all practical radio work except for long-distance communication involving the ionosphere. Even then, it can be expected to apply to results averaged over a reasonable interval of time, even though it cannot be depended upon to be exactly correct at every given moment. The Rayleigh-Carson theorem shows that in radio communication between two fixed points, the same behavior as to signal strength, optimum frequency, etc. is to be expected, irrespective of which end of the circuit is the transmitting end and which is the receiving end. The theorem also provides a means of relating the transmitting and receiving properties of antennas as discussed in section 2321. Problems and exercises. Chapter 23, Antennas. Radiation from a doublet antenna. Induction fields. Characteristics of wire radiators remote from ground. Current distribution in wire antennas. Radiation characteristics of a resonant wire remote from ground. Radiation characteristics of a non-resonant wire remote from ground. Directive gain of antennas. Arrays of antennas. Radiation characteristic of a pair of spaced antennas. The broadside array. Broadside array with tapered current distribution to minimize side lobes. Rhombic antenna. Effect of ground on the directional pattern of ungrounded antennas, image antennas. Effect of ground on directive gain of ungrounded antennas. Grounded antennas. Arrays of arrays. Radiation resistance and radiated power. Impedance and mutual impedance of antennas. Antenna resistance and efficiency. Antenna impedance. Mutual impedance. Voltage and current relations in systems involving coupled antennas. Measurement of mutual impedance. Calculation of directive gain. Radiated power and directive gain in terms of self and mutual impedance. Approximate calculation of directive gain from lobe dimension. Impedance matching and phase systems. Sorry, that's impedance matching and phasing systems. Phasing of radiators in antenna arrays. Balanced to unbalanced transformation. Miscellaneous antenna systems. Corner reflector. Directional systems involving parasitic antennas, Yagi antennas. Closed-spaced arrays, supergain antennas. Loop antenna. The turnstile antenna. Dielectric rod, polyrod antennas. Antenna systems employing parabolic reflectors. Feed systems for parabolic reflectors and representative examples of parabolic antenna systems. Horn antennas. Lens antennas. Slot antennas. Broadband considerations in transmitting antennas. Practical transmitting antennas. Behavior of antennas when receiving radio signals. Reciprocal relations between receiving and radiating properties of antenna systems. Problems and exercises. Chapter 24, Radio Transmitters, Receivers and Communication Systems. Amplitude modulated transmitters. Negative feedback in amplitude modulated transmitters. Frequency modulated transmitters. Frequency modulated transmitters for very high and ultra high frequency bands. Frequency modulated transmitters from microwave frequencies. Negative feedback in frequency modulated transmitters. Radio telegraph transmitters, amplitude on-off keying, frequency shift keying. An alternative to on-off keying is to use one frequency for the mark intervals and another for the spacing intervals. Such frequency shift keying can be obtained in many ways. The most common method is illustrated schematic in figure 24.4. Here the frequency used is the sum or difference frequency obtained by combining the output of a crystal oscillator with the output of a 20 kilocycle oscillator associated with a reactance tube that is controlled by the keying signal. Frequency shifts of the radiated wave used in practice are usually in the range of 500 to 2000 cycles. If frequency multiplication is used, the actual frequency shift of the 200 kilocycle oscillator will be correspondingly less. Frequency shift keying is used in all radio telegraph systems employing automatic printing equipment. Its advantage over on-off keying for such applications arises from the fact that being a frequency modulation system, it possesses inherent discrimination against noise and is weaker than that noise that is weaker than the signal. A characteristic that is very helpful in reducing errors when operating automatic printing equipment. Key clicks, radio receivers, general considerations, specification of receiver characteristics, receivers for particular applications, receivers for standard broadcast band, receivers for amplitude modulated signals at shortwave and higher frequencies, Frequency modulation receivers for very high and ultra-high frequencies. Miscellaneous techniques and considerations of importance in radio receivers. Automatic volume control. Tracking and alignment of circuits for single dial tuning. Spurious responses in superheterodyne receivers. Image signals. Triple detection receivers. Receivers with automatic frequency control. Receivers with crystal-controlled local oscillators. Adjustable selectivity. Tuning indicator. Single sideband systems. Diversity systems for minimizing consequences of signal fading. Space diversity. Frequency diversity. Receiver noise. Noise figure. Receiver noise and its minimization. Noise considerations in practical receivers. Noise and interference reduction in frequency modulation systems. Suppression of tube and circuit noise weaker than the signal. Minimization of noise pulses. Common channel interference. Wideband versus narrowband frequency modulation. Minimization of noise in amplitude modulated systems. Comparison of amplitude and frequency modulation systems with respect to noise and interference. Pulse systems of communications. Might read that section. This is comparison of amplitude and frequency modulation systems with respect to noise and interference. It is now possible to draw some interesting comparisons between amplitude and frequency modulation systems. First, it is to be noted that with frequency modulation, a desired signal that is moderately stronger than circuit and tube noise will suppress the latter almost completely and thus give an extremely high signal-to-noise ratio in the receiver output, even when the actual signal-to-noise ratio at the input to the final detector is quite low. No such characteristic is possessed by amplitude-modulated receivers. However, when the desired signal is only slightly stronger than the average noise level, then amplitude modulation is superior to frequency modulation because of the sputter effect referred to on page 963. Second, amplitude and frequency modulation systems are equally able to suppress disturbances introduced by noise pulses, provided the receiver bandwidths are the same. However, the ability of a frequency modulation receiver to suppress pulse noise is reduced seriously if the receiver is mistuned slightly. See page 964, whereas no such need for exact tuning exists in the amplitude modulated case. Third, a frequency modulated receiver has the ability to suppress almost completely an interfering signal that is only slightly weaker, irrespective of whether the signal is in the same channel or on an adjacent channel, whereas an amplitude modulated receiver will only suppress such an interfering signal when the difference in frequency between the desired and undesired carriers is greater than the highest modulation frequency contained in the desired signal. Last, but by no means least, amplitude modulation stations can be assigned channels differing in carrier frequency by twice the highest modulation frequency, even though wideband receivers are employed. Thus, the number of amplitude modulated channels may be assigned to the same frequency band that would be occupied by a single wideband frequency modulation transmitter. When these considerations are all taken into account, it is found that the difference between amplitude and frequency modulation is not as great as is often believed. In general, for high-quality service where effective suppression of even weak background noise is desired, as in broadcasting, wideband frequency modulation is superior to amplitude modulation. However, where a higher background noise level can be tolerated, as when intelligible but not entertaining speech is to be transmitted, the relative merits of frequency modulation versus amplitude modulation employing a wideband receiver with limiter are not greatly different. Hence, although frequency modulation is employed in most very high frequency and ultra high frequency radio telephone systems, amplitude modulation is sometimes chosen instead. Okay. Pulse systems of communication. Time multiplex. Signal to noise ratio. Practical pulse communication systems. Pulse code modulation. Problems and exercises. Chapter 25, television. All right. Elements of a system of television. Scanning sequence interlacing. Synchronization. Standard signal for television transmitters. The television camera tubes. The image orthicom. The Vidicon. Flying spot scanner. Frequency band and resolution. Television transmitters. Shall we see what it says about resolution? The detail of a television picture in the vertical direction is determined by the number of scanning lines, since graduations in the light intensity of the image in the vertical direction that take place in a distance less than the width of a line obviously cannot be reproduced. Resolution in the horizontal direction is similarly determined by the rapidity with which the television system is able to respond to abrupt changes, that is, by the frequency band and the television system transmits. The frequency band required by a television signal conforming to the United States standards can be estimated as follows. Assume that in scanning a horizontal line, the transition from black to white is to be accomplished in a distance along the line equal to the spacing between adjacent lines. With 485 active lines in a picture and a width to height ratio of 4:3, this distance is 1 over 485 times 1.33 equals 0.00155 of the active length of one line and corresponds to a time interval of 0.08 microseconds. From equation 9.1, it follows that a video system which will permit the response to rise from a minimum to a maximum in this length of time without overshoot must have a bandwidth of not less than 4.375 megacycles. A larger bandwidth than this will give greater horizontal resolution. A reduction in the bandwidth degrades the horizontal resolution. It will be noted that these bandwidths in all cases are easily adequate to transmit the synchronizing, equalizing, and blanking pulses. Television transmitters. Standard television channel. Radio frequency system of television transmitter. Video system and the composite video signal. The transmitting antenna. Television receivers. Separation and reproduction of sound, intercarrier sound system. Video amplification and DC restoration. Contrast control. Receiver sweep circuits and their synchronization, separation of synchronizing signals. Automatic frequency control for horizontal sweep generators. Brightness distortion and gamma. The relation between the brightness of an element and the reproduced image and the brightness of the corresponding element in the original scene, termed the transfer characteristic of the television system, is normally plotted on log paper as illustrated in figure 2519. The slope of the transfer characteristic is called the gamma of the system and is denoted by the symbol gamma. Color television, fundamental concepts of a three-color system. Color television transmitter. Reception of color signal on monochrome receiver. Three-color picture tube. Shadow mask color tube. The chromatron color tube. Color television receiver. Demodulation of chrominance sidebands. Reverse compatibility. Synchronization of receiver subcarrier oscillator. Receiving antennas. Multiple path phenomena. Problems and exercises. Chapter 26, Radar and Radio Aids to Navigation. The term radar is derived from the phrase radio detecting and ranging. Radar is essentially an echo ranging system in which the radar transmitter sends out energy in the form of periodic pulses of very high power but very short duration. Objects such as aircraft, ships, mountains, buildings, etc. reflect some of this energy back to the transmitter. The time delay of a returned echo is a measure of the distance to the reflecting object, since for a wave traveling with the velocity of light, each microsecond of delay corresponds to a round-trip time of travel over a path 492 feet long. The direction of the reflecting object can be obtained by the use of directional transmitting and receiving antennas. Elements of a radar system. The radar equation. It's a lot of parts. Distance to target, equivalent cross-sectional area of target, transmitter power peak, echo power peak absorbed by receiving antenna, power gain of transmitter antenna relative to isotropic radiator, power gain of receiving antenna relative to isotropic radiator, wavelength, capture area of receiving antenna, aperture area of receiving antenna. A on A0 equals a constant having a value of about 0.65 for parabolic antennas and 0.9 for mattress antennas. Radar performance factors. Radar transmitting systems, modulators. Radar antennas. Antenna scanning. Rotating joint. Lobe switching. Effect of ground on radar antenna characteristics. The duplexer. Radar receivers. Automatic frequency control. Indicators for radar receivers. Deflection modulation. Intensity modulation. Electrical coordinates. Cathode ray tube characteristics. Automatic tracking radars. Moving target indicators, MTI, and suppression of permanent echoes. The Doppler effect associated with moving targets. MTI systems. Continuous wave and frequency modulation radar. Frequency modulation radar, FN altimeter. Radar beacons. Beacon applications. Low RAN. In LORAN, which is short for long range navigation, high-powered pulses are sent out from 2 transmitting stations. A constant known time difference is maintained between the instance of departure of these pulses, so that the time difference of arrival of the pulses from the 2 transmitters as observed at a receiving point becomes a measure of the difference in distance of this receiving point from the 2 transmitters. A particular difference in distance corresponds to a receiving point located somewhere on a particular hyperbola. This is because a hyperbola is the locus of points that differ in distance from 2 fixed points by a constant amount. A station at a third location can now be used to determine a second hyperbola, and the intersection of which with the first hyperbola gives the position of the receiver as shown in figure 2618. Radio range, long wave radio range. Aircraft landing systems, instrument landing systems, ground controlled approach, radio direction finding, loop direction finders, errors in loop bearing, night effect. A loop antenna will give correct bearings only when no horizontally polarized downcoming waves are present. The reason for this is that such waves induce voltages in horizontal members of the loop that do not cancel out even when the plane of the loop is perpendicular to the bearing angle of the radio wave. The result is then either a false... I've got a phone call, excuse me. Sorry, phone call. I'm just trying to get this book finished. We're nearly done. So where were we up to? I'm not sure. Goniometer, direction finding by lobe switching, and problems and exercises. And that should bring us to the end. It does indeed. We won't flip through. Yeah, we won't flip through the index because it's too big. We've got a name index. So this is people that are mentioned. Gee, a lot of people mentioned. Wow. And then the subject index. Just flip through it here quickly. Man, these pages are tricky. It's a mattress antenna. I've never heard of a mattress antenna before. And that's it. That's the end of the book. We made it all the way through. I'll throw over the farewell cam. We'll wrap up. And that's a wrap. So, yeah, that was a fun read, wasn't it? That was the 4th edition of Terman's book, as we figured out at the beginning there. So just a little bit of a sort of rundown on what electronics was and radio was like in 1955. They were already talking about color TV. How advanced. So that's the end of this video. I hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe.